This video is on factors that will affect a rate of reactions. So there are 5 different factors, 5 different things you can manipulate or that can be manipulated that can change how fast a reaction occurs. So we'll start with temperature. Okay, so temperature increases your kinetic energy, which causes more molecules to have that minimum amount of energy required. So we talked about in a previous video, that's that E sub A, okay, your activation energy. So more molecules will be beyond that E sub A minimum. So, and then a general kind of rule of thumb is that for every 10 degrees Celsius increase, you will double your reaction rate. All right, so if we look at this graph right here, and I suggest you draw this in. So we've got our energy on our x-axis. So as we go left to right, our energy increases. And on the y-axis is just our number of molecules with energy. So we talked about in a previous video with the Maxwell-Boltzmann constant. The area under the curve is your molecules in your reaction. So in this, if we draw like an E sub A in here, let's do it in green. Okay, let's say this right here is our E sub A. All right, so what we can look at is under the red line, so the lower temperature. Under the red line, we've got this many molecules. This is the area under the curve that's reacting. All right, so then when we look at the higher temperature, 310 Kelvin, we're adding to that the red hash marks there, we're adding all of this also. So you can see we have more molecules that are beyond that E sub A. So more molecules for higher temperature. All right, and just to make sure we understand, anything that has an E sub A, so lower than the E sub A, any molecules, so like this way, okay, they won't react. Right, and anything above there can. So it doesn't mean it will, but can react, right? The will they was in that collision theory video talking about like geometry and things like that. All right, so another factor is concentration. So if you increase your concentration of your reactants, you'll increase your rate of reaction. So direct relationship. More reactants, more faster rate. Like this should be as simple as if you have more molecules, there will be more collisions. Okay, so don't overthink this. More molecules, right? Higher concentration would be more moles of solute. You'll just have more collisions, which can allow for more quickly things to react. So the third variable is particle size. So if you decrease the particle size, you will increase the rate of reaction. So we're decreasing particle size, we'll make it go faster, increase our rate of reaction. So this is really important when reactants are in different phases. For example, when you have a solid that's reacting in a solution. And this is true for things that are dissolving as well. So it increases the surface area is Y, and which allows for more contact and a higher probability of collisions. So let's say I have one solid chunk of zinc right here. Okay, so I've got this solid zinc. All right, so the reaction can only happen with the molecules on the outer edges. Oops. So any of the molecules that are on the inside of that cube there, they're not going to be able to react with anything until the things on the outside have reacted. So it's going to happen more slowly because you're going to have to go kind of like layer by layer. Whereas if you had the same mass, so if you could take that zinc chunk and put it into much smaller pieces, now you've got a lot more surface area. Where you're going to allow more molecules to be able to react, right? Because then you've made your area, your layers bigger. All right, so particle size. The smaller the particle, the more the surface area, the faster it will react. Think about like dissolving. If you put a sugar cube in water versus granulous sugar, the granulous sugar will dissolve more quickly. Versus if you take that granulated sugar and you grind it up into powdered sugar, that will react even more quickly or dissolve even more quickly. All right, so the fourth one is pressure. Pressure can change your rate. And this is just for gases here. So increasing your pressure will increase your rate of reaction. So if you have a higher pressure, you'll have a faster rate of reaction. So what this does is if I draw this container, all right, and I'm going to say like this is the top, it's sealed. All right, so here are my gas. I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules, let's say. Okay, so here's my container. What if I take this container and I compress the gas? So same container, but I'm going to take it and I'm going to push down with this plunger thing here. Okay, so now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at what's happening here. My volume decreases and my pressure increases because I've just taken the space they've had and I've made it smaller, which means you're going to have more collisions. This goes back to gas laws when we talked about that, and this is Boyle's law. Right? Pressure and volume are inversely related. So increasing the pressure, another way of saying this is decreasing the volume. That is the same thing. All right, the fifth thing we can talk about that will affect, the last one that will affect your rate of reaction is what's called a catalyst. And if you're in biology, you've actually talked about this a little bit, and I want you to make note of this, that when you hear the term, or if you remember the term enzyme, that's a biological catalyst. Okay, so a catalyst is a substance that increases the rate of reaction without itself undergoing a chemical change. So catalysts don't get used up, like they're not a reactant or a product, they just speed it up. And what they do is they provide an alternate route with, and this is the key right here, a lower activation energy. So they lower that hump. So in this first example here, or the first diagram, I should say, the first graph, all right, we have an enthalpy diagram for an exothermic reaction, right? Your reactants start higher, they lose energy, so your reactants are lower. Or sorry, your products are lower. So if you look at the blue line, without a catalyst, this is your activation energy. This is your hump. So this is your E sub A without catalyst. Okay, so just your normal reaction. So when you add that catalyst, what it does is it takes that hump and it makes it lower. So your activation energy is much lower, so it takes less energy to put into it to get it to react. If we look at this like the other graph we were drawing before, that Maxwell-Boltzmann one, we've got our number of molecules on the y-axis, we've got our energy on the x-axis, and we're not changing temperature, right? So here's our line. But look at what the difference here. Here we have our lower E, well, let's go here first. Here's our E sub A for no catalyst, right? So you only have these molecules that are going to react. Here's your E sub A for a catalyst. And now you're adding in all of these in addition to those green ones. So you're just moving that mark over so it's easier to get that amount of energy. So these are the 5 factors you need to understand what they are and why they can change your rate of reaction.